This second video and its corresponding homework problems has to do with the counting principle. The counting principle is pretty easy to state. When there are m ways to do one thing and n ways to do another, then there are m times n, or the product of m and n, ways of doing both. So let's take a look at an example. Let's say you have three different shirts, and we'll call them A, B, and C for the purposes of simple writing. And you've got 4 pairs of pants, 1, 2, 3, 4, and you want to count how many outfits you can wear. Well, one way to organize your effort would be to say, I'm going to think about what happens if I wear the first shirt, A. Then I could wear the first pair of pants, or the second pair of pants, or the third, or the fourth. Similarly, if I use B as my shirt, then I could have the first pair of pants, second, third, fourth, and lastly, if C is the shirt, I can have that shirt paired with the different pairs of pants. And so it looks like I have 12 possible outfits. And you can see that the way I've done this, there are kind of 3 groups of 4. Here's a group of 4, here's a group of 4, here's a group of 4, 3 groups of 4. Counting principle says if you have 3 ways to choose your shirt and 4 ways to choose your pair of pants, then you have 3 times 4, or 12 ways of doing it together. So let's take a look at another example. Let's say I have a set with 3 elements in it, A, B, and C, and I want to know how many different subsets there are. Well, when I go to make a subset, I have some choices. I can either choose to put A in the subset or not. One way or the other, yes or no. Same with B, yes or no. Same with C, yes or no. So I have 3 yes or no decisions. For my first yes or no decision, there are 2 things I could choose, either to put A in the subset or not. For my second choice, I have 2 more possibilities, either put B in or not. And for my third choice, I have 2 more possibilities. So the counting principle says there will be 8 subsets. And those subsets are the empty set, and then the set that includes A, the set that includes B, the set that includes C, my set notation is kind of lousy, I apologize, the set that includes AB, the set that includes AC, the set that includes BC, and the set that includes A, B, and C. Listing them is a little bit difficult, but the counting principle is pretty easy. Let's look at another example. Let's say we can use some 2s, 3s, and 5s multiplied together to build as many different numbers as we can. And with the 2s, we could use 3 of them, 2 of them, 1 of them, or none of them. And with the 3s, since we only have 2 available, we could use 2 of them, 1 of them, or none of them. And with the 5s, we could use 1 or none of them. And we're trying to figure out how many numbers we could build using those pieces. So using the counting principle, it looks like for the 2s, we have 4 possible choices. 3 2s, 2 2s, 1 2, or no 2s. And 2 to the 0 power is 1. It's not 0. So if we chose none of them, we wouldn't have 0, we would have 1. With the 3s, it looks like we have 3 choices. 2 3s, 1 3, or no 3s, 3 to the 0 power. How many choices do we have with the 5? Well, we can either put it in or not. It's a yes-no thing. We've got 2 different choices. And so there are 4 times 3 times 2, or 24 different numbers we can make. And listing them is a little bit tricky. Let's see what happens if we try to list them. So if we multiply these 2s and 3s and 5s together, we get 360. So the numbers we can build out of the 3 2s and 2 3s and 1 5 are the same numbers that are factors of 360. So we can list all the factors of 360 in ordered pairs, 1, 360, 2, 180. They're nice and in order, so we can easily count them and see them. And there's 12 pairs, so that's 12 times 2, that's 24. Notice this is a pretty easy way of figuring out how many factors a number has. Let's try another one, maybe a slightly faster, easier one. So let's say we're finding all the different factors in the number 36. And so we do a prime factorization. 6 times 6, 2 times 3 times 2 times 3, 2 to the second times 3 to the second. The counting principle says we have 3 choices with the 2's. We could take 2 of them, 1 of them, or none of them. And we have 3 choices with the 3's, 2 of them, 1 of them, or none of them. The number of choices we have is always 1 more than the exponent. And so there are going to be 9 different factors when we list all the factors of 36. So we have 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6 and 6. But we don't need to list a factor twice. And so there's the 9 factors that the counting principle predicted. Now let's do a couple problems that are like your homework problems. So we have Sam's Limited Sandwich Shop, and we're going to build a sandwich, and we want to see how many different kinds of sandwiches we can build. And so there's 3 different types of bread, and you can't choose none of them. You have to choose one of them. So how many choices do you have? Well, you have 3 choices. You have 2 different types of meat, but you can choose one of those 2, or you can choose none. So you could choose one kind of meat, the other kind of meat, or no kinds of meat. So there's 3 choices. You have 4 different kinds of cheese, but you can choose none of them. So that gives you a 5th choice. There are 3 yes or no choices, mustard, mayo, or salt. So that'll be 2 to the 3rd power, 2 times 2 times 2, because there's 2 choices for each of those. So that's 2 to the 3rd power. So it says write down how many sandwiches you can make as a product. Well, it's going to be our 3 times our 3 times our 5 times our 2 to the 3rd. And that looks a little sketchy because we have 3 times 3, and that could be 3 to the 2nd times 5 times 2 to the 3rd. Now we're supposed to multiply it all out. We could use Wolfram Alpha or a calculator to multiply it out, but this is small enough that maybe we can multiply it out on our own. So this is the answer to part A, and part B would be 9 times 5 times 8, and 8 times 5 is 40 times 9 is 360. So this is our good friend 360. In the second problem, we're going to use the prime factorization of 84 to help us predict how many factors it has. And then once we know how many factors it has, we're going to list all the pairs of factors in order. So first we're going to get the prime factorization. It looks like 2 times 42, 2 times 6 times 7. The 2 is good, the 7 is good, but the 6 breaks apart into 2 times 3. Sorry about that, but when I press weirdly on the screen, strange things happen. This is not working out as well as I would think. So I'll be more careful. There we go. So we have 2 to the 2nd times 3 to the 1st times 7 to the 1st. So when we multiply, with 2 to the 2nd, we have 3 choices for the 2's, 2, 1, or none. 3 to the 1st, we have 2 choices, 1 of them or none of them. And 7 to the 1st, we have 2 choices, 1 or none. And so we have 3 times 4, which is 12. So 84 is going to have 12 factors. Let's try to list them. 1 and 84, 2 and 42, 3 and 28, 4 and 21, 6 and 14, and maybe 7 and 12, and that looks like 12 of them, so I know I'm done. Those are the 12 factors that are predicted by the counting principle. Kind of neat.